So let's move on now to the one of the main tasks for the day is to relate the Hamiltonian and the angular momentum, not just classically, but in their full quantum mechanical sense. And the hint as to how to do this, of course, comes from our classical analysis. So we are going to try to do this now quantum mechanically. So in quantum mechanics, if we were to carry out the same calculation, we're now going to look at the operator associated with the square of the angular momentum, which of course is defined as just the sum of the squares of the corresponding operators. And I want to be careful here to remember what is an operator. So I'll be drawing a lot of hats. As the lecture goes on, I may forget some of the hats, but I hope from context you will know which pieces are actually the operators. So this just says sum the squares of the corresponding components. And each of those components we know we can get from R cross P. But remember now, these are operators. It's the R operator gathered together into a vector, cross with the P operator gathered together into a vector. This cross product then will give me three different results. The first one will be Lx, the second Ly, the third Lz. And this expression tells me to apply the X operator twice in a row, and then to do that for the y and the z and add them all together. But that is precisely what the dot product means. So our job really is to evaluate this operator expression. Now, at first sight, this notation might seem a little bit confusing because I've got both vectors and operator hats. So let me just remind you exactly what I mean by these. The R vector hat really just means I'm going to make a vector out of the three corresponding coordinates. So the way we normally would do that is the x component of this vector is my x component. I can write that either as r1 times I hat, right? Or also, sometimes we like to label these x, y, z, because I could also, of course, call this x times I hat. But what I'm really saying is I'm identifying r sub 1 with x. And then there's the second component of r sub 2, which would multiply j hat to make a vector. But of course, that's really representing y times j hat. So I'm calling y r2, and likewise the same thing for the k hat direction and the third component. Now, the reason why I actually prefer, and these are operators, r1 hat, r2 hat, r3 hat, I prefer, and you could think of these as operators x hat, y hat, and z hat, but of course, finally, we know that those operators in the position representation, which is what we will be using, are really just the corresponding coordinates. So these are really three different ways of looking at this vector. The utility of this upper way of looking at it is simply that, well, there's going to be a lot of summations going on here, and if I want to sum over x, y, and z, it's easier to have the same variable name and just a subscript 1, 2, and 3. Corresponding to this, I guess there's really a fourth way of writing this vector, right, which would be simply to say, well, the operator associated with r1, which is like the x hat operator, really in the position representation is just the variable x, or I'm just going to label that r sub 1, I, r sub 2, j, plus r sub 3, k. So, finally, to re-summarize, because it's important we get these clear in our heads, this is the operator expression for the R vector. This is what it would look like if I just wrote it out as x, y, z, but I prefer the R notation because I can then do sums over the different coordinates. And this is the actual real space coordinate representation of that operator. So that's the R operator. The P operator is a little bit more complicated, but it follows the same general spirit. So I'll have P vector hat, right? And that, of course, would be then the Px operator, which I can also call the P1 operator, times I hat, plus the second P operator J hat, plus the third P operator in the K hat direction. And if I want the coordinate representation of this, Of course, I could start writing px, py, and pz, but I think we're already used to the idea we're going to be using numerical indices to distinguish our coordinates. The next piece is to express these operators in the real representation. Now, I want you to notice that for any of these, for instance, the p hat n operator, that is, if written out in terms of the coordinate representation, that's h bar divided by I times the derivative then with respect to the corresponding coordinate, which we are calling r sub n. So the other way really of writing this would be to pull out the h bar divided by I term. So I'd have h bar divided by I, and then what is appearing inside of here is actually, the derivative with respect to the first coordinate times I hat plus the derivative with respect to the second coordinate j hat plus the derivative with respect to the third coordinate k hat. And of course, as we complete these preliminaries, R1, R2, and R3 are really just d by dx, d by dy, and d by dz. And this whole operator combined together is just known as the del, or the gradient operator, h bar on I times del. So we have our operators in the coordinate representation, so we can think of them that way, or we can think of them as their corresponding operators. Very good. Now that we've got the operators all spelled out, let's continue on with our analysis. So what I have is this quadruple product among these operators, but what I have to help me to do this is this key vector identity. So I'm going to rewrite these now using this vector identity. But there is, I'm going to leave a little extra space here. You might want to do that in your notes because there's a lot of thinking that's going to go on. There's going to be a lot of math coming up now. The payoff of this will be we will understand the Laplacian operator, but we've got some work to do to get there. Now, when I use my identity, right, I'm supposed to dot this r with this r, and then dot the p with the p. The problem with that, though, is this expression is doing it for just normal classical variables which commute with each other. When I write down my identity here, I have to be very careful not to commute this r past this p so I can take its dot product with itself. So I want to be extremely careful about this. So I'm going to leave a little space here, but then what I'm going to do is I'm going to write my operators in their proper order. There's an r operator, a p operator, another r operator, and another p operator. And my job is, for the first term here, is I have to take the dot product of these first two and then multiply it with the dot product of these next two. So to take the dot product of the r with the r, this r with this r, I have to do that without moving the r past the p. I have to keep the p in between them. And the way I can do that is to simply put my index over n here and then sum this over n. Yes, that will give me my dot product, and I've at least preserved the fact that the p has to be in there. The second piece of my job is to dot product this p with this p over here. So I have to get these two dot product with each other, but I can do that. I can do pm, pm, and then also sum on m. So that is how I handle my first term. Now there will be additional terms, so I'm going to open up a parentheses. It's going to be a rather big, long parentheses, so let's just draw the beginning parts of it. Okay, now, second term. So the second term, I have to subtract off. Now it's going to be very similar logic. R hat, p hat, r hat, p hat. I have to preserve the order of my operators. And now I take the dot product of this r with the p that's over here. So that's all the way across. So that would be rn, pn. And then the dot product of the second p with the second r. I mean the first p with the second r. So that would be pm, r, m. So I'm not going to close my parentheses yet because I want to put in some additional terms here, as you will see. But I hope at this point you can identify that the terms I've written down are the proper translation of this vector identity into the quantum mechanical context. Now, when we look at these pieces, you notice, of course, they are not in the proper order that I was hoping for, right? The classical order really gave us a nice intuitive picture and allowed us to isolate p squared, which is the key piece I need to get to energies, because then I can just divide by twice m. So in order to get a p squared term, I do have to finally move this p operator next to his friend over here. So I want to rearrange the order of this term. And we learned in previous lectures exactly how to do that when we were playing with the simple harmonic oscillator. The trick here is to write down the commutator symbol, right, which is going to allow me to swap the order. So this will preserve the original expression so long as I now add back the term that gets subtracted, which is the reverse order term, which would be then r hat n, p hat m, p hat m. So I've succeeded. Now I really have the dot product of r times the dot product with p. So this term looks good. He's done. So I can get this term now into exactly the classical form. There's just this extra piece here, and this is the cost coming from quantum mechanics. Let's move on now to the second term. My goal here is to get this r dotted with this p and this r dotted with the other p. So this pn has to move its way all the way to the beginning of the expression. So once again, we know how to make these move. We put in the commutators, right? And then we add on the term in the reverse order. Now, of course, the whole expression on this piece is coming in with a minus sign. So when I add that term on, it comes actually out subtracted. So that would be minus r hat n, p hat m, p hat n, r hat m, which is getting there, but he has to move again. So I know how to do that. I can commute those two. And then that will give me minus r hat n, p hat n, p hat m, r hat m, which is close, except classically, I really like this idea of having r dot p repeated twice. So I've got my first r dot p, but this is p dot r, so this is also backwards. So I need yet another commutator, and then I have my final piece, r hat n, p hat n, r hat m, p hat m. Now I feel brave enough that I can close my parentheses finally. It's quite a collection of terms we've generated. Now, as we'd said, these two pieces are the ones we want. Those are the classical pieces. These other pieces with the commutators, these are the quantum mechanical parts. So for these quantum mechanical parts, I need to know what the value of these commutators are for the various terms. So let's look at those one at a time. Let's look at this commutator first. So if so this is a side note, right? If I have a commutator of p hat m with r hat n, if I think about what this is, p hat m, that is h bar on I times the derivative with respect to the mth coordinate, so that's r sub m, and that's being then commuted with r hat n is just, this is m, this is p hat m, r hat n operator in the position representation is just the coordinate r sub n. Now, for a commutator such as this, we can always pull out the constant h bar on I, and now I have to do the commutator of the derivative with respect to rm with actually rn. Now let's think through what this is going to be. So I've got h bar on I. Now there are two cases here, right? If m and n are different, then this is something like, for example, d by dy commuted with the variable x. Now, the way partial derivatives work, all of my coordinates are constants with respect to those derivatives. So I can always pull x out of any y derivative. So it doesn't matter what order I write these in. So if I have different coordinates here, I'm always going to get 0. So this value that I have is going to be 0 if n is different from m, and I have the perfect function to do that. I can write that as a Kronecker delta nm, so that I'm guaranteed to get 0 when n is not equal to m. Now I'm not done. I haven't figured out what happens if n equals m, so I have to look at that case as well. Now, if n equals m, this would be something like d by dx commuted with x. And we had seen this in the harmonic oscillator. This commutator is actually just positive 1. So I have to make sure that when n equals m, this term just gives me 1 times h bar on I. But the Kronecker delta is perfectly defined to do that. When n equals m, it actually does give me 1. So this is my answer for that commutator. Wonderful. Now we can use this to begin to analyze my various terms. This term here is going to be therefore h bar divided by I times delta nm. Right? 1 if they're equal, 0 if they're not. This term looks very much like the preceding term, except notice it's in the reverse order. When it's in the reverse order, it picks up a minus sign. So this is minus h bar on I times delta nm. So that will be that commutator. Now, this one, I think, is pretty interesting. We haven't seen that one yet, so let's look at that. So if I'm commuting two different momenta, so if I had p hat m commuted with p hat n, each of my p hats will give me a factor of h bar divided by I, so there's going to be two of those factors I can pull out. And then I'm looking at the commutator of partial derivatives with respect to various coordinates, Rm and Rn. Now, let's just think about this. Suppose I have the two coordinates are equal to each other. Well, that one's easy, right? That either order I write that in, I get the same thing, which is the second derivative. So that commutator is 0. If I try commuting two different variables, d by dx and d by dy, well, then what I get is the partial derivative with respect to x after I do the derivative with respect to y, subtracting off doing the derivative with respect to y, acting on the result of doing the derivative with respect to x. But because for normally behaved functions, mixed partial derivatives are always equal to each other, this commutator also is 0. So if n equals m or n is not m, it doesn't matter. Two momenta always commute with each other. Therefore, this term at least gives me a nice 0. And the final term I'm left with is this one here. Now this looks just like my first term. The only difference is that n now equals m, but I can use the same general expression. There's nothing preventing me from doing that. So this would be h bar on I delta m, like so. So we've got now all of our pieces. Our job now is to kind of, consolidate all of this work that we've done and to compute the various related sums.